So yesterday we looked at research methods. We began a discussion on research methods, and I went through the different research methods. Can you remind me, can we remind ourselves some of the research methods we looked at yesterday? I would like to see it type in the chat. Anything you remember from yesterday? Okay, thank you, Clarissa. Case study, okay. Joan remembers qualitative. Okay, the quantitative method, right? Thank you, Rebecca. Thank you, Jeremy. Survey method. Okay, so today we're going to talk more about the survey method. We're going to look at the survey method in detail. And we're also going to finish looking at experimentation. All right, thank you, Jacinta. Maybe just a brief recap. So this is this slide. Yesterday, I labored to explain indeed the different methodologies, the qualitative, quantitative, and the combined. And we say that under qualitative, each of these methodologies have methods, the quantitative and the qualitative, there are methods there. And yes, you've mentioned them. We said there is survey, we said case study, looked at action research. And so we're going to finish up a little bit on experimentation, and then we shall go into detail. We shall look at survey in detail. That's what we are looking at for this first part. All right, where we were yesterday. So just look at experimentation, and then we'll go to survey in detail. So experimentation is one of the quantitative ways of doing research. It is a typical research method used in natural sciences. We are talking food science, biology, physics, where you will have an experiment, like just like how used to be in the physics lab, something you set up and then you see what will happen. They may involve definition of a theoretical hypothesis. That is, there may be a statement that maybe this is, if I put this liquid in here, it will turn like this. And then a selection of a sample, allocation of sample, and control on other variables. So saying that, okay, if you put this liquid in this one, it turns, and you don't put in this one, it will not turn. And then you see what happens. And then in light of IS and software engineering, we also have these experiments, and they are classified. We can have a lab demonstration whereby a researcher uses a product on a realistic example within an artificial environment, the artificial environment being the lab. So if you have developed your product, let's say you've developed an app and you use it within the lab and you test how it performs in the lab, that's a lab demo. And then field demonstration is where the researcher or designer uses the prototype or the product within the field. So again, the researcher is with the product in natural environment in the field and sees how it behaves. And then we have lab experimentation, where others use the product in an artificial controlled environment to achieve the goals set by the researcher. So it's not the researcher using his or her product, but there are other people using it within a lab. And then field experimentation, the researcher gives the research product to others to use it I need to correct this. It's not now. It's not under controlled condition. It's in the field. Need to correct this. So the researcher gives the product to others to use it within the field to achieve goals set by the researcher. So that is experimentation. So for our course, we have looked at only two quantitative methods. That's the survey and experimentation. Now we're going to look at the survey in detail. The next part of the lecture. Yeah, so we're going to look at this, at the survey research method in detail. I hope that's what you're all seeing. So when you're going to conduct a survey, you need to plan. You need to plan, because remember we said that with a survey, you have a big population, and out of that big population, you get a sample. The small sample is going to represent the big one, and you want the results that you get from the small sample, or the data you collect from the small sample, to be able to represent the big, to be able to represent the population. And because of that, to be able to do this, you need to plan. You need to plan how you'll sample. You need to plan the method you will use and the data collection method you will use, or the data collection tool you will use. So you need to plan how shall you collect the data and from whom shall you collect the data. And then you carry out the survey, you process results from the survey and interpret the results. So since it is often expensive to cover all units in a population, the sample is studied. And the sample can be studied and the results from the sample used to infer the population of used to infer to the larger population. However, the success of any research project depends on the way in which you select the units or the objects to participate in the study. So how you select the sample is very important. It is vital to know that the various ways of selecting units that are going to participate in the research survey, that is sampling. So it is important to know the different ways of sampling. Good sampling techniques maximize the degree to which the selected group represents the population. Again, this is what you want to achieve. You want the selected group to be able to represent the population very well. The population is a group of potential participants to whom you want to generalize the results of the study. The sample is a subset of that population. When the results can be generalized from sample to population with a high degree of confidence, then these results have a meaning beyond the limited setting in which they are originally obtained. Let's say you wanted to study, you want to know about youth, so you sample some youth. Now, if the results you get from these youth can represent very well the entire population of youth, or the youth, then they have meaning beyond just that small population. Indeed, if these results can represent very well youth in Uganda, they could as well represent youth in Kenya. So the results can serve a greater purpose if the sampling process was done well. So before selecting a sample, the population should first be divided into non-overlapping parts that are called unit or sampling unit. Then a list is made of these non-overlapping parts, or a list is made of the sampling units that is called a sampling frame. What do we mean by not overlapping? We mean that every element in the population should belong to one and only one unit. The unit can be an individual person, can be a firm or an organization. Basically, before you sample, you should know, okay, the sampling unit is an individual. So you have the population divided into individuals. This sampling unit should be non-overlapping, meaning every element should belong to one and only one. Of course, for people, it is clear to see what non-overlapping means. A person can only be one person. You cannot be one person and you two people, or you cannot be the same with two people. So that is simple. If you're going to survey hospitals, then each hospital is different, is an entity in its own sense. You shouldn't have people belonging to two hospitals. That's what we mean that there should not be an overlap. And then generalizability of results is very important because if the sample is not an accurate representation of the population, then the results you get are not generalizable. And if the results are not generalizable, then they're applicable only to the units that were sampled. And then you lose the purpose. Because remember, survey is for studying a big population. So if you cannot generalize your results from the sample, you lose the purpose. In every survey, it is important to assess whether the sample selected from the population appears to have all the characteristics of the population in the same proportion. In that effect, the sample will be considered a mini population. And we're going to look at how you do that. Okay, so the purpose of sampling is to make inference to a population based on a smaller sample. And this I've said that again. So we're going to look at the different ways of sampling. First, we have probability sampling. Probability sampling is where the likelihood of any one member of the population being selected is known. And in this case, you can have random selection. That is, a selection of the participants is determined. It can be determined by chance. So the selection can be by random rules or non-random rules. We're going to look at them. But the key thing with probability sampling is any one member in the population has a probability of being selected. That is known. And the number keeps going up. All right. Okay, I've seen. I'll not wait next time. I'll start early. Then that means you people join earlier. Those who are just joined us. Bear in mind, I wait for us. But next time, I think I won't wait so that we can start early. Now, I've seen. I will not wait next time. I'll stop waiting for us to log on. I just start. As soon as we are 5, I start. Then so that you don't just join in as we go on. But okay, I was talking about the probability sampling. We're going to look at the different probability sampling strategies. And then we have non-probability sampling, where the likelihood or probability of selecting any member from a population is not known. Therefore, potential members of the sample do not have an equal and independent chance of being selected. So under the probability sampling, we have simple random sampling, and it can be with replacement or without replacement. With simple random sampling, we shall look at it in detail, that you just pick randomly. And you can pick and replace back, or you may pick and not replace. Then there's systematic sampling, stratified sampling, and cluster sampling. Let's begin by looking at simple random sampling. With simple random sampling, each member in the population has an equal and independent chance of being part of the sample. Equal chance in the sense that there's no bias, that one person should be chosen rather than the other. So it doesn't matter if one is male or female, young or old, every person is the same. Is the same and any can be chosen. Then independent chance being independent chance because the choice of one person does not bias the researcher for or against another person. So if the researcher chooses a male, that doesn't mean that next time they will not choose a male. They can still choose a male. If the researcher chooses a female, they can as well choose a female again next time. So the chances are independent. That is simple random sampling. In this sampling, the characteristics of the sample are very close to that of the population, as in what you're interested in studying. Each sample has it, and so it appears like the characteristics of the sample are very close to that of the population. There's a process of how you do this. You first define the population that you want to select. Then you list the members of the population. Then you assign a number to each member of the population. And then you use a criterion to select the sample you want. You may choose a random table or you may choose SPSS. Now, let me just add the video here. I wanted us to watch. I thought maybe we shall watch it later, but let's first watch it. Because some things I'm saying, you'll see them better in the video. Let's first watch this video. And I'll play it, we shall watch it together. All right, slowly coming. Oh, let me see. Put it in the chat. Okay, it's taking long. Oh dear. Sorry, it's taking a while.
A lot of the frameworks and methods I teach are...
Just a minute, it's not the one. Okay, just
Return it to Word! Project Manager, ClickUp has really helped with mapping out timelines and priorities. Makes everything run smooth. What hasn't been as smooth is our transition back into the office. Faster! Okay, faster! Whose kid is this? Hey, Brett, can we talk about...
Okay, that video has come.
Recall that a population refers to the group of things that we want information about, and the sample
Okay.
Recall that a population refers to the group of things that we want information about, and the sample refers.
Let's do that again.
Refers to the group of things that we want information about, and the sample refers to part of the population that we take out to examine and draw conclusions from. In this video, we will be looking at the different methods of obtaining a sample. But first, let's look at the types of biased samples. Biased samples occur when one or more parts of the population are favored over others. The two types of biased samples include the convenience sample and the voluntary response sample. A convenience sample only includes people who are easy to reach. If this is our population and a researcher comes along to interview people, then he would only talk to the people that are closer to him to be part of the sample. This is a biased sampling method because not everyone in the population has an equal chance of being part of the sample. Only people that are of convenience to the researcher will be interviewed. Now, a voluntary response sample consists of people that have chosen to include themselves in the sample. So the researcher lets people come to him. This is a biased sampling method because people with a strong interest for the survey topic are the ones who are most likely to respond, whereas the people who don't feel as strongly about the topic may not even care to respond. Remember that a good sample is one that is representative of the entire population, and it gives each thing an equal chance of being chosen.
Okay, so what the video has first explained are the non-probability sampling methods, the convenience and the voluntary response. They are non-probability. Each member of the population did not have a known chance even of being chosen. So you see with convenience, it's just those who were near, and voluntary response is just those who came. So those first two that he explained are non-probability sampling methods.
When you have these conditions, you have what is known as an unbiased sample. We will be looking at three different types: stratified random sampling, multi-stage sampling, and simple random sampling.
Okay, so this what he's calling unbiased sample is the probability sampling method. Remember, we said that with probability sampling, each member of the population has a known chance of being selected. And these are what we have started looking at now.
The most basic type of sampling is the simple random sample, also known as an SRS. Since an SRS is unbiased, each individual has an equal chance of being chosen to be surveyed. In other words, to be part of the sample. You can think of an SRS as putting names into a hat and selecting N of them. So if I wanted a sample size of 6, I would select 6 papers and come up to the randomly chosen people to interview them. For a stratified random sample, we take the population and we divide it into something called a strata.
All right, if you noticed in the simple random sampling, everybody was the same. The researcher just picked, regardless of the color, everybody was the same. But here, with stratified random sampling, you see they have first divided the people into groups. So stratified random sampling, you use it when the characteristics of the people matter to the research that you're studying. And so you have to first separate them into strata, and then you can just continue the video.
Strata refers to the groups of similar people. Within each stratum, we take an SRS and combine the SRSs to get the full sample. For example, we could take an SRS of 2 people from each group so that we get the total of 6 people. A stratified random sample is good for making sure that whoever is administering the sample gets in contact with each kind of group. The last type of sampling is called multi-stage sampling. For multi-stage sampling, we use a combination of 2 or more simple random samples. As the name suggests, multi-stage sampling means you have to go through different stages to find where your sample comes from. For example, if we have 3 groups, stage 1 could be selecting which group will be picked using an SRS. Let's say that I picked out group 1. Then that means I would only look at group 1. Then for stage 2, I would do another SRS to get the 6 random people. We go through different stages of simple random samples to get the actual sample, and this is why this is called multi-stage sampling. I'd like to point out that instead of putting names in a hat, there's another way to pick things randomly. We can use something called the random digits table. The random digits table consists of a long string of random numbers, and it can help us do an SRS. To use it, I would first have to label each member of the population with a number. We have 30 people in this population, so I will label each person from 1 to 30. Notice how I have written 0, 1 instead of just 1. Doing this helps us use the random digits table. Since each label has 2 digits, we will read the string of numbers 2 digits at a time. So let's say I want a sample size of 4. We will use the random digits table to randomly select 4 people. The first number on the table is 19, so person 19 will be part of the sample. The second number is 22, so person 22 will be part of the sample. The third number is 39, but our sample size doesn't go up to 39, so we will ignore it. We will also ignore 50 and 34, but we will keep number 5. We will also ignore 75, 62, and 87, but we will keep number 13. As a result, these are the people we would survey.
All right. So I'm hoping that you have seen at least simple random sampling, how it is done in detail of it. That's why I wanted us to watch that video. It just makes it very, very clear, very beautifully clear. Okay, so the video explained simple random sampling, and I just spoken about it. And then it never mentioned systematic sampling. So systematic sampling is a way of sampling systematically, where every case name on the list of the target population is chosen. So remember, you have your list, so you organize the population. And then you choose now every case name. The steps involved in determining the systematic sampling are as follows. First, you determine the size of the population. And sorry, you decide or you determine the size of the population, N, capital N. And then you also need the sampling size, the small n, such that your value K will be N, big N over small n. Example, if population is 100 and the desired sample size is 25, then K will be 4. So then you'll be choosing every 4th element in the list. And here you can see that each member of the population has an unequal chance of being selected. It's unequal. Though it is there, they have a chance, but it is unequal. It's not like with simple random sampling, whereby every member of the population had an equal chance of being selected. With systematic, the chance is not equal. And then we have stratified sampling. Now, you use this method if the characteristics of the population, the specific characteristics of a population are of concern to your research you're doing. If you're going to carry out a research that is religious, you want to find out attitudes of different religions, you need now to factor in that your population is made up of mixed religions. It is just not the same. You see, with the simple random sampling and the systematic sampling, it's assumed that like everybody in the population is the same as the other. But stratified takes care of that people are not the same. So if individuals in the population are not equal in terms of features, then stratified sampling should be used to ensure that the profile of the population matches the profile of the sample. Let me say that again. If individuals in the population are not equal in features, then stratified sampling should be used to ensure that the profile of the sample matches the profile of the population. So in the video, that's when you saw that, at first you start when the colors are mixed, and then now for stratified sampling, you have to separate the colors. Stratified sampling is used when factors that distinguish the population member from another are related to the subject you're studying. Such factors may include gender, race, religion, etc. Stratified sampling ensures that the strata all layers in the population are fairly represented in the sample. Therefore, the sample becomes also layered like the population. I hope in your mind you can just remember that in that video, after I did the stratified sampling, you have 3 colors now in the sample. So in order to carry out stratified sampling, first the population is divided into 2 or more mutually exclusive segments based on the categories or varieties of interest. So if you're interested in gender, then you'll have the population divided into two groups, male and female. If you're interested in age, then you may divide the population into maybe 10 to 20, 20 to 30, 30 to 40, like that. These layers represent the different characteristics, and they should be non-overlapping, and they should collectively make up the population. Each layer is called a stratum for single, and all the layers are called strata, plural. The stratifying yields homogeneous samples of the population before sampling is done. Then after that, a random sample is drawn from each stratum. So if use SRS to get from each stratum, then the whole sampling procedure will be called stratified random sampling. No, I think I will have to go through that again. So if you, for example, you had a population that was mixed of students, grade is the same as primary. So if you have, let's say P6, you had them together, P6 along with P5 and along with P4. To carry out stratified sampling, you'd first have to separate them. You have P4 alone, P5 alone, P6 alone. And then from each of these, you do a simple random sampling. As you notice, simple random sampling, we use it when the population is assumed to be the same. As you can see here, they're all 4th graders, so you can just pick any. Then lastly, there's cluster sampling. Now this one, the video did not explain it. Did not explain it. Cluster sampling is used when units of individuals are selected rather than individuals themselves. So however, the unit of analysis is different from the primary sampling unit. And I'm going to explain what that means. I'll explain that through an example. So assume you want to study the challenges faced by doctors in Ugandan hospitals, and a conclusive list of all the doctors is not available for you to use the SRS. So what you do, you first obtain the whole list of the hospitals. Now the hospitals are the clusters. Remember we said cluster, you use units of individuals rather than individuals themselves. That's what the cluster is, a unit of individuals. So you use a hospital. Now the hospital will be the clusters. So you get a list of all the hospitals. You randomly select a number of hospitals, say N. So before you had a big list of hospitals, let's say there are 4,000 hospitals. Then you do random sampling and you select 100 of them. Then from these 100 hospitals, you determine to maybe get four doctors from each, so that you can now make up your total sample. So the units in the population must be homogeneous enough so that any differences in a unit do not contribute to a bias. Meaning, let's say if you want to study for the hospitals, the type of doctors that you have within each of the hospitals should be the same, such that it's fine, it's okay. You'll still have the same kind of doctors in each of the clusters. So what this sentence means that, however, the unit of analysis is different from the primary sampling unit. So with cluster sampling, the primary sampling unit is the cluster, but the unit of analysis is the individual. Just like here we saw, we first had to get the hospitals, but then we are finally collecting data from individual doctors. So here we have an example of stratified sampling. Let me explain this very well. Just a second. Did I go back? Oh, I went back. Sorry. Yeah, so we have an example of cluster sampling. You have the big population, you divide it into clusters. Here, each symbol represents religions. So you divide the population, but each cluster has a mix of the religions. And then from there, you randomly select any of the clusters, and then you'll have your final sample. Then lastly, we have the the non-probability sampling methods. These are now what the video called biased. They're biased in the sense that they cannot represent the entire population, and anyway, they don't want, let me say they don't want to. So these, you might wonder, why do we have these non-probability sampling methods if they are biased anyway? But there are situations where you need them. So purposive sampling, one of those is purposive sampling. This is used when there's a need to study something about or features of a specific group of people. So you're looking at a specific group of people to start with. You don't want an entire population. You just want a specific group of people, and you want to study some of them to represent them. So if you're going to study health hazards of miners, there are miners, let's say, working in a coal mine or working in a coal mine. There are just a few. There will be a few. You'll have to go specifically to the coal mines, and you look for those people. That's why it is purposive. You just won't find anybody. If you're studying dangers of health hazards of prostitutes, you will have to look for specific people who are in that category. You just cannot go find anybody on the street and ask them things about prostitutes. That's what purposive is. And then we have convenience sampling. It's the easiest way to select a sample where respondents are a captive audience, whereby, yeah, if people are interested, you can easily get from those who are near you. The sample generated is not a random sample, as in, you do not really mix them up, just like you saw there in the video, just the people who are near came. The sample you get may not represent the entire population, or it may represent only to a small extent. So if you wanted to study the youth, and then you say, well, I think if I go to the park, I'll find a mix of youth. I mean, there'll be both male, female. Yeah, there shall be those from up country and those who are, around town. So you go there. What you get, you may not get a good representation. You won't be the same as somebody who looked for those from the rural areas and looked for those who are male or female, who did that kind of mix. But yeah, some convenience sampling is used. It's the easiest and the fastest way. Then we have quota sampling. This is suitable when you need a sample that is stratified on certain variables, yet proportional stratified sampling is not possible. So you find yourself that you cannot exactly do stratified sampling as it is supposed to be. You cannot divide the population such that you have male separated alone and female separated alone. And then you cannot do that, but yet you want to represent these different characteristics. So you do quota sampling, whereby you say, all right, I'll first, if I can get 40 male, then I can get let's say 20 female, then I can mix it like that. So that is what quota sampling is. So it's also a non-probability sampling method. I shall link for you to go through those examples. This one, you shall go through them along on the slide. So next we'll look at how to determine the sample size. So we have seen how to get the methods. Yeah, so we have seen the different sampling methods. So now the issue is, how do you determine the sample size? So there are mainly two approaches, two ways of getting the sample size. One The first one is to use a table. There's a certain table that I'm going to show us that can just show you what the size is. The second one is to use a formula, and then you calculate it. The one for using a table, all you need is to know the population size plus the sample size. Sorry, all you need is a population size. Then the table will tell you the sample size. That's how the table looks like. If your entire population is 10, then the table says the sample should be 10. So for such a small figure as 10, you have a census, as in let the whole population be the sample. If the population is 15, let the sample be 14. If the population is 70, let the sample be 59. If population is 500, sample is 200, like that. Population is 50,000, sample is 381. So that is a quick way by using this table. Then the other way is by using formulas. So when you want to get the sample size using a formula, there's some parameters that you need. You may need the population. Then you need the sampling error, whereby sampling error is the error that occurs in survey results due to studying a sample instead of the whole population. So sampling in and of itself introduces an error in the process just because you never sampled the entire population. So there's an error, an inherent error, but this error has to be acceptable. And then you need also to know, you need to say what is your desired level of accuracy or confidence. How confident you want to be that this sample of yours represents the entire population, and there are values for that as well. Then also your formula, the formula that you use will depend on the type of statistical value that you're looking for. Are you looking for population mean, or are you looking for the proportion? Lastly, your sample size does depend on the budget. So no matter what you've calculated, finally your budget dictates what to do. And yes, even if you looked at the table and the table told you 300, but your budget can't do 300, then you may reduce the sample size. So let's look at now how to calculate the sample size using the desired statistical value. And I've said that there are two types of statistical values we're looking for. We could either be looking for the mean of a given feature, let's say the mean age, mean weight of the population, mean income. The equation used is different from one whereby you want to know the proportion of the population. So you may want to know a population proportion, that is the percentage of individuals who fall within a category. So you want to know of this population, which group of individuals fall into this category. And we're going to look at how that works. So we'll first begin at looking at statistical mean. So if what you want to find out is the mean of a certain value, then the equation that you use for sample size is Z over A squared. Simply that, where Z is a number relating to the desired degree of confidence. Typically, the values we have can either be 95 or 99% confidence. And if you, for whichever level of confidence you want, there's a corresponding Z value. And this Z value is that Z value that we did in those statistical tables when you're learning statistics in S6 and S5 there. I'm hoping you remember those lessons, that you'd have that graph and then you're looking either for normal distribution or what. There's that Z comes from there. And then E is acceptable error in your results. You may say, well, an error is, and sampling error of 5% would be okay. That's really the error that they normally use. Then next we have the equation. If what you are looking for is a proportion or a percentage of something. And here, Z is the same Z in the previous equation. E is also the same E that we had there. But there's a new parameter called P, whereby P is an estimate of the proportion of objects falling into the target group in the population. So of the population, what percentage or what proportion of objects fall into what you want? That is the thing. And then we have 1 minus P, which is usually represented as Q. It is just one take away P, that same P. So altogether you have your equation. If you're to compare with the previous equation, what you're adding here is this P and 1 minus P, just that factor. Yes, Apollo, if you had run away from math, it has come for you, but don't you worry. It's not as complicated as it appears. They're just a few equations. Yeah, they're just a few equations. And I'm trying to show you that if you compare the two equations, this was just Z over E squared. This is still, you'd have this E here. It's almost the same Z over E squared, but with this multiplied by this P and 1 minus P. So let's look at an example of that, of how you use the proportion. This Z, this first one of mean is very simple. Very simple. Just get the values and put them there. That's simple. But just an explanation of how the unfold proportion works. So supposing we wish to evaluate a statewide extension program in which farmers were encouraged to adopt a new practice. Assume there's a large population of farmers, but we don't know the variability in the proportion that will adopt the new practice. So there are so many farmers, we don't know how many will adopt the new practice or adopted it. Therefore, we assume a proportion P that is equal to 0.5. So that is half, 50%. We assume that they say, okay, maybe we want to know that 50% adopted that new practice. And then we propose a confidence level of 95. Same, we want to be 95% confident in our results. And then we propose, we have a sampling error of 5, plus or minus 5. I shall answer the question in the chat just after this. So then we just fill in our values. The Z value corresponding to the 95% confidence is put there. The error is there. Then this is P, and this is 1 minus P, and you have the number of farmers. Notice in this case, we don't have a population here actually. We don't know the number of the population. Yes, Maurice, research does have math. We are going to, especially in data analysis of the quantitative type. Yes, there's calculations. All right, so let's just watch maybe a video on. So I've talked about how we calculate sample size. Let's just watch a small video. Let's watch a survey. Sorry, my YouTube is taking a while. I've posted it there in the group. Yeah. All right. Let me first continue. I think when my internet finally responds, I shall watch the video. Oh, that's come.
What? Still searching YouTube for math help? Are the videos from 2006 really helping? Aren't
to my easy statistics. In this video, I'm going to discuss about how to determine the sample size.
I forgive the presenter, his Indian accent. Bear with it.
Sample size is determined in two steps. First, calculate the sample size for infinity population. Second, adjust the sample size to the required population. This is a formula which we use to calculate sample size for infinity population,
Come again?
where S is
We are not seeing the video.
the population.
Oh, okay.
We can't hear anything.
Oh, phew. Sorry.
Welcome to my easy statistics. In this video, I'm going to discuss about how to determine the sample size. Sample size is determined in two steps. First, calculate the sample size for infinity population. Second, adjust the sample size to the required population.
Okay. Now,
This is a formula which we use to calculate sample size for infinity population.
okay. Now, this equation right here is just what I've given us. And yes, it is called that one for an infinite population. You don't have there in these parameters there. There isn't n, the population size, it's not there. And so the m is what it is E, and the Z is a Z, and everything is just the same as we have just seen.
The S is sample size for infinity population. Z is Z square. P is population proportion. We assume population proportion as 50%, which is 0.5. M is margin of error. Z score is determined based on confidence level. And confidence level is defined as the probability that the value of a parameter falls within a specified range of values. Is a table which gives the confidence level and the Z value. If we consider the confidence level as 95%, Z value is 1.96. And margin of error is defined as a small amount that is allowed for in case of miscalculation or change of circumstances. Generally, the margin of error is considered as 5%, which is 0.05. M is 0.05. Z score is 1.96 at confidence level of.
Okay, so those values that he has said, it's like Z can either be 395 or 90 or 99. The margin of error, EOM, is always taken as 5%, and the proportion is also taken as a half.
95%, P is 0.5, M is 0.05. If I substitute all the values in the given formula,
okay,
the sample size for infinity population is 384.16.
So bear in mind, that means that for whatever kind of research it is that you're going to do, as long as the confidence level is that, and E will always be 0.5, proportion will always is mainly 0.5 also. So the sample size is 384. Even in our example, you saw that it was 384.
So the sample size for infinity population is 384.16. Now, second step, we are going to adjust the sample to the required population. For example, we want to adjust the sample size to the required population of 1 lakh.
100,000. Now, forgive the Indian
we use the following
language.
formula for adjusted sample size of population 1 lakh. This is a formula. When I take S value as 384.16, which is sample size of infinity population, and population as 1 lakh, I get the adjusted sample size for 1 lakh population as 300.
Okay. Now, as you can see, the difference is very small. Yeah, all the extra math just led to this. A difference of 1.
82.69, which is approximately 383. Finally, we have determined the sample size for required population of 1 lakh, which is 383.
Okay, so I hope you have seen that it's not all that complicated. What we have just seen, what we just learned in class was the sample size for an infinite population. And when you adjust it to suit a large population, the difference is just 1. And if I could just take you back to this table of ours. The first table, where is it? Morgan's table. Yeah, just something I want you to see from that table. This, if you are paying attention to that video, the man after he calculated for 100,000, the answer was 383. It's like after a certain number, the sample size doesn't vary much. If you to look at this, so anyhow, that is sample size, and I'm hoping you're no longer afraid of the math. It is very simple. Then we have the sampling error, and this is the error there's an error that comes about because of a discrepancy between the sample and the population, and it can actually also be calculated. So the smaller the value of the sampling error, the less the discrepancy between the sample and the population. The higher the sampling error, the less generalizable the results are. The less generalizable the results are. If the population N is less than 100, then a census would be suitable rather than sampling. Remember, I tried to show you from the table. If the number is small, it's much better that you just use the whole number so that you avoid having this error. But it's an inevitable error. It has to happen because of sampling. In computing sampling error, there are two critical factors that are considered: the size of the sample and the statistical value being measured, whether you're looking for mean or you're looking for proportion. And if we had been looking for a proportion, the sampling error is calculated with this equation. E is a sampling error, S is now the sample size, Z is a desired confidence level, and P is the proportion. Now I'll allow you to you take some time and see whether if you just get the square root, you can get E from the other equation, but that is how you calculate sampling error for proportions. Lastly, we have understanding what sampling error versus sampling bias. So sampling bias is mainly experienced in non-random samples, where the survey findings represent opinions of individuals or groups within the population. Sampling bias can also arise if volunteers are used, or if you use convenience sampling. So basically, that's the idea that sampling bias comes in at the type of method you use. The sampling method you use can introduce a sampling bias, how you do the sampling. Otherwise, sampling error will happen for any sample. It happens just because you have sampled. That is what it is. So that's how the two are different. The sampling error versus the sampling bias. Sampling bias can be avoided by sampling right with the right kind of sampling method. The sampling error cannot be avoided, or it can only be avoided by using a census. So the only way you avoid sampling error is by not sampling. But you can avoid sampling bias by using a good sampling method. Okay, so at least we have looked through. Basically, if you're designing a survey, you have to determine the target population. Then you select the appropriate method that you shall use. Then you calculate the sample size. You determine the acceptable sampling error. Of course, now determining the error and confidence level will all be part of, you'll use them in calculating sample size. And then you determine the suitable data collection techniques that you shall use, and you're good to go. You're ready to do your research. So you might have a small break. Let's just watch one video as we have a small break. Okay, I just move video and go for a small break.
Billion peanut butter M&Ms manufactured every year. How many of those do I need to look at to have a high statistical probability that I know exactly the mix of different colors that they manufacture? Hi, I'm Jen, and today I'm going to be talking about sample sizes. Most of the time when we talk about statistics, we're not able to get measurements on every single part of the population that we need to measure and understand. Populations can be large, sometimes infinitely large, and in some cases, the ability to gather every piece of information is incredibly difficult. In our case, we're going to look at peanut butter M&Ms manufactured in the US. To have a chance at understanding this information, we're going to look at a video of a larger population that represents the population as a whole. Ideally, we always want a random sample. This means that every single member of the population has an equal chance at being picked, and picking one member of the population has no impact on picking another member of the population. Truly random samples are incredibly difficult to find because it normally isn't possible to really get this randomness. I picked up a bag of M&Ms that has 159 M&Ms. While this bag has an assortment of different M&Ms, there are limits to its randomness. First, it's just one single bag, and by selecting that bag, I've predetermined what other members of the population are going to be in it. These M&Ms are also manufactured at multiple different plants, and this bag is only from one plant on one day and one time of a production run. So it really isn't truly random. The sampling I'm doing is called availability sampling. It's trying to pick a population that should be somewhat representative, but it's based on what's available. It's one bag from one grocery store in my area. To show you how big of a difference the bag that you select can make, I also picked up two other bags. I picked up the small bag that you would see at the checkout, the sharing size bag, and this gigantic party size bag. These each have different number of M&Ms and very different mixes of colors. When we start with a very small sample, look at the mix that's in this bag from the checkout. If I thought that this sample was representative, I'd be assuming that yellow is a very rare color in a bag of M&Ms. But if we look at the next size up, we see the color variation looks a little bit different. It looks a little more evenly divided. And as we go to the biggest bag, we see it evening out even more among the colors. We can easily take this medium-sized bag worth of M&Ms and understand a lot about that medium-sized bag. There are a few different issues we need to contend with when trying to take the results of looking at a sample and apply them to the entire population. We need to make sure our sample is representative of our entire population. You can really see how different this is when we compare the 3 different size bag of M&Ms and how their mix changes. Since it would be both expensive and very time consuming for me to obtain a truly random sample of M&Ms manufactured throughout the US, even if I selected just a 1-year time period, I'm going to have to make some assumptions. I reached out to the company, and while they wouldn't share the percentage of different colors that they manufactured, they did tell me that everything was mixed together and then the bags were filled by weight. Since I know the colors are mixed and then filled by weight, I at least have some chance of this being somewhat representative. Even though the bags are filled by weight and everything is mixed together before filling, the smaller the sample size, the more likely that we're going to see some variation from our true population. Samples that are representative are also called unbiased samples. Let's look at how to calculate the sample size we need if our sample was truly random. First, we'll look at how to calculate sample size for an infinite population, and then we'll adjust this when we have a finite population. For really large values, there's going to be very minimal difference. The formula for sample size of an infinite population is z squared times the population times 1 minus the population over m squared. Z is the z-score, and we can get that from a table based on our confidence level. The confidence level is the probability that the value of a parameter falls within a specified range of values. So let's say we want the result of.
Okay, we can pause it there. She's going to tell us the same things we have seen. At least I hope you appreciated from my explanation just how, if your sample size is small, you can easily have an error, and also how you can, how you can easily have an error. That's why the advice is that if your sample, if your population is small, then it's better you do a census, so you just avoid errors. But the rest of the video is much the same about the equation that we did, so we shall not go over that. So I hope we have all learned and sampling size, sample size calculation and sampling very well. For the next part of our class, I want you now to tell me at least what's going on in your work, because for now I've added on to you more knowledge. Now we have begun ideally what will be the 3rd chapter of the proposal if you're writing it. And it's quite a lot, so I want to first know where you are at. So let's have we shall have a small break. Let me see the time. We shall have a small break. And then when we come back from the break, I will ask you what's going on with your work. I told you to come ready to share something. Let's stop sharing here. Oh, before we go there, do I have any questions? Are there any questions? All right, so I'm going to give you some, it is 3:40. I'm going to give you some 20 minutes. Prepare to tell me something on your work before we can even go further. Yeah. In your groups, prepare to share with me something on your work in this next 20, we start at 4. So I'm giving you some 20 minutes. Tell me something, what's going on with your work? First, stop recording.